In challenge set 23 about transformations, you were asked to post your solution to question 11. And question 11 says that for each of the graphs in the previous problem, add the graph of g of x, which is a transformation of, of each of these four functions. It says that we're going to add the graph g of x equal to negative 2 times f of x minus 3 plus 1. And then it asks us, what transformation must you do to each of the parent graphs to get the graph of g of x? So we really have to make sure we have a nice solid question number 10 in order to get number 11. And in question 10, we were asked to basically come up with a parent function for each of these function families. And I've done that here in blue. So letter A is quadratic functions, and we've just got the function f of x equal to x squared. It's the simplest possible quadratic function. For linear functions, we've got f of x equal to x, and for absolute value, f of x equal to the absolute value of x right here. And then finally, we've got, for the square root functions, f of x equals the square root of x, which is graphed right here. So our task now is to add to each of these graphs the transformed function g of x. And I've added a note down here to help us out. And this is really most of my solution to question 11. Here's the function as it was given to us. G of x is equal to negative 2 times f of x minus 3 plus 1. And I've translated this into words. To get g of x, stretch f of x vertically by a factor of 2, reflect it across the x-axis, and then translate it 3 units to the right and 1 unit up. And that's what these 3 parameters do to the function of f of x. So let's take this quadratic function as an example. I could do this transformation with each of these 5 points. 1, 2, 3, 4, 5. And I'm going to start here with the vertex. I'm going to first stretch it vertically by a factor of 2. Well, that's stretching 0 by a factor of 2 just gives us 0. And then reflecting across the x-axis. This point is actually on the x-axis, so it doesn't need to, when we reflect it across the x-axis, it is still on the x-axis. And then translate 3 units to the right, 1, 2, 3, and 1 unit up, right there. So that's my new vertex. And let me just take another point from this function, this point right here. Let me start by stretching by a factor, vertically by a factor of 2. Well, that means I go from 1 unit to 2 units. I'm going to reflect across the x-axis, so instead of a positive 2, I'm going to be down here at negative 2 for my y value. And then I'm going to go over 3 units, 1, 2, 3, and up 1. And that puts this particular point is transformed into this point. And again, if I did that with its symmetric point over here, stretch it by a factor of 2, reflect it, move it to the right 1, 2, 3 units, and up 1. There we go. And now you can see the beginning of our parabola forming right here. Of course, if I take these 2 points, then I'm going to go 1, 2, 3, 4. I'm going to go all the way up to 8. 1, 2, 3, 4, 5. Right here. Yeah, 8. Reflect that. That goes to negative 8, which is negative 6, negative 7, negative 8. It's right down here. And then over 1, 2, 3, and up 1. And this, you may remember, and its partner is going to be right over here. This makes sense because if you notice, I go, instead of going down 1 and then down 3, the odd numbers, to get to each of these points, I'm going to double that, down 2, down 6. And so this is related to what we were doing with quadratics in our last unit. But there's the graph of g of x, and what I'm going to do is just color it in green. And I want to take a minute here to write out the function g of x in terms of x. So this is what g of x looks like here. But for us, we're squaring. Our f of x is just the squaring function. So up here I'm going to say g of x is equal to a -2, and then f of x minus 3 is just x minus 3 squared plus 1. And look, that makes a lot of sense when we look at this graph, because if you remember from our quadratics unit, what we've really done is we've just translated this parabola, or we have a vertex at 3, 1, and then to find the other points, the negative sign makes it open downwards, and the factor of 2 gives us this vertically stretched parabola. So that's g of x right there. Of course, we could rewrite it in standard form if we wanted to by multiplying it out and combining like terms. But I'm just going to leave it like this. And I'm just going to knock out these other transformations right here in the rest of the video. And it basically, we do the same thing. Again, I can take any point, stretch it vertically and reflect it, translate it 1, 2, 3 units over, and 1 unit up. That's this point. Let me do it again with another point. Stretch it vertically and reflect it. So stretch it vertically, reflect it. Let me show you again here. Stretch it vertically, 1 becomes 2. Reflect it, -2, over 1, 2, 3, and up 1. And if I could pick any point on this line, this one, -2, or -2, comma, -2. So stretch it vertically, goes to -4. Reflect it, goes to +4. Translate 1, 2, 3 units over, 1 unit up. There it is. And all of these points are going to be on this same line. And I can kind of fill them in so that I can complete my graph. But this right here is the transformed function, the transformed linear function. And I'm going to color it in here. And it might be good just to kind of, I'm going to run into my function up here, but just to notice where the y-intercept is, that might be helpful. Because when I actually write, when I use this relationship here to write my function g of x, let me just put it right over here, running out of space. G of x is equal to a -2 times f of x minus 3. But notice, if I plug x minus 3 into this original function, it's just going to be x minus 3 plus 1. And I will go ahead and rearrange this a little bit. This becomes g of x equal to -2x plus 6 plus 1, that's plus 7. And notice this green line has a y-intercept of 7 and a slope of -2. So my transformation, when I convert it, when I take the equation and I convert it into slope-intercept form, it matches just perfectly with the actual transformation that I performed graphically. The absolute value function, really similar to the quadratic, of course. I know that the vertex is, let me do it backwards this time. I'm gonna write g of x here. I'm gonna do this transformation to this original function f of x. So it's going to be -2 times f of x minus 3, which is just the absolute value of x minus 3, plus 1. And now you should recognize this from our unit on absolute value functions, that my vertex is going to be at 1, 2, 3, 1. And then I'm going to stretch this and reflect it so that it's pointing downwards, and I get this function. And again, we'll use the green to represent our transformed functions. And there's one more to go. There we go. One more, the square root function. So again, if I don't know exactly how to construct the graph of the transformed function, I can just transform a few points to see where it's going to end up. This point, stretched and reflected, stays where it is, and then translate 1, 2, 3, and up 1. This one, stretch, reflect, translate 1, 2, 3, and up 1. Right? This one here, stretch, reflect, goes to here. Oops, let me try again. This point here, stretch it, reflect it, and then translate 1, 2, 3, up 1. So here's my new function right here. And I'll just extend that right there like that. This is an interesting function because it has an end point, because you can only take the square root of positive numbers and expect a real number result. If I apply this transformation to this equation, I'm going to get g of x is equal to a -2 times the f evaluated at x minus 3, which is going to be square root of x minus 3, plus 1. And that is my transformed function. So the real value of this is to notice that no matter what our function is, we can apply the same transformation to that function in order to get really any other function in the function family. And just a few important points. Question 11 asked us to describe the transformation that we have to do to the parent function, which I did here in words. It also asks us to add the graph of the transformed function g of x to the graph that we did in question number 10. So a complete solution contains these graphs and a written explanation.